Okay, we're going to look at 2.1, limits rates of change in tangent lines. We're going to go probably in rates of change, tangent lines, then limits. Apparently they like to go in alphabetical order. Okay, I'm going to start with something you're familiar with. Slope. You are familiar with that notation. Coming from a point or 2 points, like such. Okay. In calculus, we change that notation just a little bit. Because we're going to have points over an interval. And it can be any variable, but I'll just put x sub 0 to x sub 1, noting that that's an interval. Okay? The y values or f of x values, as we're going to call them, over that interval, so the range, we'll just be evaluating that function. Okay, so what we have for points are x0 and f of x sub 0, and x1 f of x sub 1. Okay? So the way we note it in calculus, it's just a different notation. Notice that the f of x's are the y values. They're still the outputs. You can match them in the points if you want. It's just a new way to look at it. Okay. So get used to writing more formally in this notation here, because it's better. Slope is also called rate of change. With our vertical realignment of the math curriculum, you should probably know that. So a rate of change could be something like velocity. Okay, velocity is a distance over a time. It's a rate of change over time. Okay, how far have you gone in how many hours? Right. There are two concepts that you'll want to get a hold of. This is where we're going to play around a lot in this area. Average velocity is a change in position over a time interval. All right, so it would be something like the velocity over that interval from time 0 to time 1 is the change in position, change in time. So position, you're going to see a lot position this year is denoted S. A position function will be S of t. Position of a function is a position as a function of time, S of t. But this is change in S, or position, over time. So there's that position function. The function of position at time 1 minus the function at time 0. Okay. I'm going to give you an example here. The other one you need to know is instantaneous velocity. Okay. So this Average velocity would be like saying how fast did I average from Parachute to Denver if it was 240 miles and 4 hours. I actually think it's 180 miles, just about exact. I made that drive many times. So you take 180, divide by 4, and you get 45 miles per hour. Okay, so that's the average over the trip, average velocity. Instantaneous velocity would be like your speed at any moment. Okay, if you look at your speedometer, that's your instantaneous velocity. Okay. Rarely will it say 45 because you're going to go below 45 and above 45 driving in the mountains. But it's the speed at that one particular moment. Okay. This, I'm going to show you how to calculate this. Basically, it's just a very small time interval, so we'll use like 0.01 seconds here to calculate an instantaneous velocity. Okay. So it's a very small time interval. And we're going to actually do something called limits, which shrinks that time interval as close to 0 as possible. So we get an instantaneous velocity. Okay. Let's do an example. Galileo discovered that if an object is released at time 0 from a state of rest, the distance traveled after t seconds is given by this formula. So it's a position as a function of time. Let's say we have a stone released at rest falls to Earth. We're going to estimate, that's the key word there, estimate, instantaneous velocity at 0.8 seconds. Basically, what we need to do is shrink this time interval as much as possible to get a good calculation on instantaneous velocity. Let's say we try time 0 to be 0.8 and time 1 to be 0.81. It's a really small time interval, 1/100th of a second. So if we plug this in here, so t0 goes in, it's 0.8, 4.9 times 0.8 squared. 3.136. Let's try T1, which is 0.81. Which is 3.2149. Right, so we have all the numbers that we need to do our slope calculation. Now notice I've switched T0, T1 here with it different here. It doesn't matter as long as the T1s match and the T0s match. As you can see, mine do. Alright, so we have 3.136, that's the T0 minus 3.2149 over 0.8 minus 0.81. Do the math, you get 7.889 meters per second. This is in meters per second. Okay, so that's an estimate. And what you're going to find with smaller time intervals is more accurate. So if I go from, let's say, 0.8 to 0.8001, I'll have S of 0.8001 okay. What you see is we have two different numbers, but obviously since this is a shorter time interval, it's getting closer to that instantaneous velocity. Okay. What we have here is, let me just make a small table. To illustrate this for you. So we had 0.8 and 0.81. If we did 0.805, see how these are they're kind of trending down. If we tried an even smaller interval, we would get, okay, and then we're trying even smaller. So we can see that it's probably trending or approaching 7.84. This is probably a good estimate for instantaneous okay. What we're doing is we're taking this time interval towards 0. Okay. This is heading towards our instantaneous velocity. Okay. So the closer we get to 0 time interval, the better our estimate is. This whole derivatives are completely based on instantaneous. Okay. So, but what you see, this is called a limit. Okay. So the limit as t approaches 0 is the instantaneous velocity. So the instantaneous velocity is where we end. It's the limit of it. Okay. Another way to say it is the instantaneous velocity is the limit. It's the end of the average rate of, average velocity. Okay, so basically we're taking the velocity, and wherever that velocity ends, these average velocities, wherever they end is our limit. So a couple different ways to say it. Graphically, okay, let's say you have position, a velocity graph. Let's say you want instantaneous at time 3. We're going to go with a secant line. Secant lines touch twice. But that's not going to be very good instantaneous velocity. Okay, we're going to have to go to a smaller interval. It's going to be better. Right? It's going to estimate that better. But what if we went to another one? Okay, about right here. Okay, smaller time interval, again, same thing algebraically. Smaller time interval, better estimate. What we're headed towards is what we call the tangent line. It touches once, basically the time interval is 0. Okay, so it only touches that one particular point at 3, and it gives us an instantaneous. The slope is the instantaneous velocity, okay, the rate of change. Okay, so that's what we call a limit. All right, let's check out another one. Let's check out this example of the speed of sound in dry air. And this is going to be in meters per second. And it does vary. Humidity does slow the speed of sound down, which is kind of interesting, but the air is more dense. If the air is more dense, it's going to travel more slowly. Okay. This is the formula. B equals 20 root T. T is in kelvins. Okay. So we're going to estimate instantaneous rate of change, or velocity, when T equals 273. I'm actually going to show you this one on the calculator. I'll have to get one first. So put it in your y equals 20 root x. I'm going to go to, I'm actually going to use a table. So I'm going to table set my start. I want 273. And my change in table, I'm going to say, let's go 0.1 for now. All right, so we can get our numbers straight from the table. So we have a time interval, and we have average rate of change. So we're going to go from 273 to 273.1. Notice that this is from the right.
Okay, we're higher, so it's coming from the right. We're coming lower. The average rate of change here is 0.06 over, so that's 0.06 over 0.1. Now you can get more precise, so if we go set our table again to 0.01, it calculates it for you. We see our difference is only 0.01. Should be 1. Something's not right here. Maybe it's... there it is. We're not using precise enough decimals. So 330.454 to 460 is 0.06. 0.006, so that's going to be 0.6 meters per second. The other way to do it is from the left. You're going to go from 272.9 to 273, and you'll probably get 0.60528. If you do 272.99 to 273, so you're approaching from the left, you get 60523. See how they're trending smaller? So we're going toward 0.605 from the left and the right. Okay, so we can, so our instantaneous velocity is approximately 8. I'm on a video here, let me finish. Here's your work. There you go.